Okay, so let's start off with the following theorem. And the theorem is that the continuous image of a connected set is connected. So remember, we had talked before about always being concerned or interested in how continuous functions or continuous maps preserve certain properties, such as convergent sequences, compact sets. And now we have another important theorem. It tells us that continuous functions preserve connected sets. So they take connected sets to connected sets. So if we're about to prove this, let's go ahead and prove this. What would be our hypothesis? What would be our claim? Well, a reasonable hypothesis would be you have a continuous function. So let's just say here we've got f going from m to n. So m and n are metric spaces. Let's put in here the f is continuous. We also can say that m is connected. And then the claim would be that the image of m under f is connected. So f of m is connected. Now, do we remember what f of m is? F of m is the set of f of p belonging to n such that p belongs to m. Okay, so now how are we going to prove that f of m is connected? And let's suppose not. Now here's the setup. So I have a little sketch here, and we're saying suppose this is m, and this is f of m. Right, so f of m is here. For our proof, we're going to suppose that it's not the case that f of m is connected. That means, so I've drawn a picture here where I've got two components or two parts. Well, what does that mean? That means that, well, let's go back to what does it mean to be connected. So a set is connected. We have three, I've written down here three different and equivalent ways of proving that a set is connected. First is to say there's no disconnection, right? And then second, there's no proper Clopin subset. And the third is any Clopin subset is either the empty set or S. So let's use, we essentially will use there's no proper Clopin subset. So we'll say suppose not, then there exists A and B subset of M such that A and B are disjoint. Their union is equal to M, and A and B are proper, so A and B are proper subsets. And lastly, A and B are Clopin. Clopin in M. Okay. Now, in my little picture over here, we could say maybe this first one here is A, and the second component here is B. All right, now what's wrong with that? What's the problem? Well, just kidding. It's not the case that A and B are Clopin in M. We would need A and B are Clopin in F of M, right? Okay, so what does it mean to be Clopin? That means, first of all, A is open in F of M. By the inheritance principle, that means that there is an open set in N. There exists U, open in N, such that A is really U intersect F of M. right? So if we were to update our sketch here, we'd be saying there exists some u, and maybe u is in, that's u, and of course there also exists a v. And u and v are open in N, and their intersection with f of m is a and b. So let's add this to our proof here. So there exists u, and let's put v in here because we can do the same thing. B is equal to v intersect f of m. And let's just go back and modify this sentence here. So A, B are open in f of m. And by the inheritance principle, we've got two open sets in N whose intersections are with f of m are A and B. Now remember, f is continuous. What do continuous functions do with open sets? The preimage of open set is an open set, right? So since f is continuous, and u and v are open in N, the preimage of u and the preimage of v are both open in M. Now, just as a reminder, what is the preimage of u with respect to f? It's a set of points in M such that f of p belongs to u. And similarly, the preimage of v is going to be the set of points in M such that f of p belongs to v. So with our picture here, we know that we have two open sets Well, now here's the deal. What we're going to say is these two open sets actually form a disconnection of M. So that can be F pre U. And then we can have F pre V. Now, the claim is that M equals F pre U, disjoint union F pre V. In fact, now we've got to prove first, we've got to prove that the intersection is empty, right? So we want to show that it's actually these sets are disjoint. So let's see here. Q belonging to F pre U intersect F pre V would imply that F of Q belongs to U and V, but F of Q would also belong to F of M, right? So F of Q would belong to U intersect F of M, which is A, and F of Q belongs to V intersect F of M, which is B. So F of Q would belong to A intersect B. Get a contradiction because A and B are disjoint. So we know that the preimage of U and V are disjoint. Well, I don't need to rewrite it. I think it's overkill. What's another thing we need to show? We need to show that M is actually equal to the union, right? Now how are we going to show that? Well, clearly, F pre U union F pre V is a subset of M, right? And P belonging to M implies F of P belongs to F of M, which implies F of P belongs to A disjoint union B, which implies F of P belongs to U or V. Right? Because A and B are subsets of U and V, right? And now this means that P belongs to the preimage of U or the preimage of V. Okay? So, what does this mean? All of this tells us that M is a subset of preimage of U union preimage of V. All right. The last thing we need to show, so we've shown that M is the disjoint union. Now we need to show that this is clopin in M, and also that this set is clopin in M. That will give us a separation. But that's going to be easy because, let's see here, now we show that F pre U and F pre V are clopin in M, but this follows because they are both open. And F pre V is the complement of F pre U. Right? So remember, the complement of an open set is closed. So F pre V is closed. And it's open, so F pre V is clopin. Similar argument shows F pre U is clopin. Okay. Lastly, what do we need to show? We need to show that they are proper. So lastly, actually we don't need to show that they're proper. Here's what we'll do. We'll say suppose it's not connected, then there exists A and B such that, here we go. This is what we're going to use. We're going to use the fact that A and B are proper subsets. I think I messed this up. Let me see. I need A and B subsets of N. Sorry. A and B subsets of N. Right? Such that A disjoint union B is the image, F of M. Did I not write that down somewhere? Okay. All right. I think we're good. Now, A and B are proper subsets. So that is going to, when we pull that back to M, we'll get that these preimages are also proper subsets. And that'll give us a contradiction. Since A and B are proper subsets of F of M, so since A and B are proper subsets of F of M, there exists say P in A, and there exists Q in B, right? So that's how we know that both of them is neither empty nor all of f of m. So there exists an x and a y, and well, let's see, there exists an x. Let's go back to our picture here. So here's the idea. The idea is if we have, excuse me, so if there's some point P here and some point Q here, then there has to be x and y such that f of x is equal to P, right? F of x equal to P and f of y equal to Q. Because if P is in f of m, then there's some point in m that is mapped to P, right? And that point is in the preimage of U, since P is in U. Similarly for Q. So there exists x in f pre U. There exists y in f pre V, such that f of x is equal to P, f of y equals Q. So f pre U and f pre V are proper subsets of M. So we have a disconnection. So M is disconnected, and this is a contradiction. Contradiction to hypothesis. Right? So it must be the case that f of m is connected, right? So our proof, we said suppose f isn't connected, then we'll have a separation of f of m, right? Suppose f of m isn't connected, we'll have a separation, and when we pull back with that continuous map, the preimages form a separation of m. Okay, so that's essentially it. So f of m must be connected. All right. So now we know continuous image of connected sets are connected. And let's just give a proof that R is connected. So this is the metric space. We should be very used to it. In this situation, M is equal to R, and D is just absolute value, Euclidean metric, okay? So we're going to show that R is connected, and we'll have a sketch. The sketch of the proof is as follows. Again, suppose not. If R isn't connected, then that means that there is some subset of A that is clopin and proper, right? So now, once we set this up, this means, of course, that R equals A, and then disjoint union A complement is a disconnection. Or sorry, it's a separation. Getting my terms confused. I sound like Oprah Winfrey. Is a separation. Yeah? Now, number one, if A is clopin, that means that A is open, right? In R. And I can't remember if this is from homework, but we said every open subset of R is a union of, in fact, actually a countable union, but a disjoint union of open intervals. So this might have been from homework, And if it wasn't from homework, I'm not going to turn this into a homework problem because I'm aware that we have an exam, but you should definitely think about this and give it some thought and come up with a sketch. Every open set in R is the disjoint union of some intervals. Open intervals. Right. So in this case, we're saying there exists some open intervals such that A is the disjoint union of the open intervals, right? That's because A is clopin. Now, since A is proper, that means A is not equal to all of R, right? So A is not equal to all of R. So one of these intervals has to look like, one of the I alphas has to be of the form like this, or could be a bounded interval, right? So it could be unbounded or a bounded interval. One of these intervals has to be of this form. Otherwise, A is all of R, and A is an empty set. So we don't have that. Now here's the deal. Look, if we've got this, beta is the endpoint of one of the I alphas, so beta belongs to A complement. If A is clopin, that means A complement is open, right? So now imagine, let's just say, suppose we have this scenario, right? One of the I alphas looks like beta comma infinity. So then that means beta belongs to A complement. So there is supposed to be an R ball, beta minus R, beta plus R, that is contained in A complement, right? But notice that's going to be impossible because if here's beta, for any R, right? For any R, we are now dipping into that I alpha. So remember, the I alpha is going like that, right? And what do I mean? I mean the I alpha, that interval contains all the points greater than beta. So there's no way that you can have a positive radius where that R ball is not intersecting or overlapping with I alpha. So we get a contradiction because A complement can't be open. Because remember, what does it mean to be open? Every point has an R neighborhood completely contained in that set. Okay? So this is a sketch of why R is connected, right? And now we can couple these two theorems. The first theorem says that the continuous image of a connected set is connected. The second theorem says that R is connected. We couple these to get or to conclude that 0 to infinity is connected. What's an easy way to do this? Proof. So I'm spelling in a very unique way here. Put the R first. All right, so here's our proof. F is going to go from R to R. Just take X and send it to X squared. Then F is continuous. M is connected, right? Because we just proved that. And F of M, which is equal to our goal here, that closed unbounded interval must be connected. So we're able to get a lot of connected sets. And if you remember, we actually came up with continuous functions from class to describe almost every single one of these scenarios, right? And we came up with continuous functions from R to each of these intervals. So we use the previous two theorems to conclude any interval of this form of one of these, uh, in one of these formats, is connected, right? So that's the power of having proof theorems that say connected image, a continuous image of a connected set is connected. It opens up the whole, right? It allows you to easily conclude that a set is connected. Okay, a lot easier than going back to the definition. All right, we are moving along at a fast pace here. Let's see here. Generalize intermediate value theorem. So remember we discussed that we would have three value theorems. The first was the extreme value theorem, second, intermediate value theorem, and the third, which we'll get into in chapter 3, the mean value theorem. So each time we've got functions, the codomain is R, real values, real numbers, and we're just talking about the behavior of a certain type of function. So here we are saying if your function is continuous and it goes from some metric space to R, then that function has the intermediate value property. What does it mean to have the intermediate value property? IVP, intermediate value property. It means that your function is going to attain all intermediate values. Now, what does that mean? Let's look at a picture to show you. So here's what we mean. I mean, if you have a point, this is M, and clearly, or hopefully you get that this over here is supposed to be R. Okay, so what do we mean by F? If F is continuous, F is going to attain all of the intermediate values. Suppose you have 2 points, P and Q and M, and they're sent to F of P and F of Q. Without loss of generality, assume F of P is less than F of Q. What we're saying is, for any point gamma, so any point gamma in between F of P and F of Q is the image of some point in M, right? So there exists some X such that X is sent to gamma. Okay? So we're going to do the proof. The proof is suppose not. So in other words, suppose F is continuous. F goes from M to R. M is a metric space. P and Q are in M, right? And suppose F of P is less than F of Q. Now imagine what would happen if there was a gamma in between F of P and F of Q, but no point in M was mapped to gamma, right? So this is our suppose not. Then there exists P and Q and M, and there exists a gamma in R, such that gamma is in between F of P and F of Q, but no point in M is mapped to gamma. So gamma is not in F of M. Then here's what we have. We have a separation. Our separation is going to be this set here, a separation of F of M. And this set here intersected with F of M. So did you get that? We're going to take, so let's just verify here. So we've got negative infinity to gamma intersected F of M. Disjoint union F of M intersected with gamma, the interval from gamma to infinity. All points bigger than gamma. All right. Why is it disjoint? Because that should be clear. So we'll say because there's no overlap. So suppose we call this first set A, and this intersection here, suppose we call it B. Now, why is it disjoint? Because A is going to be a subset of negative infinity to gamma, and B is going to be a subset of that interval, right? So A intersect B has to be empty. Now, why is F of M equal to the union of A and B? Well, if you have a point, if x belongs to M, then f of x belongs to R, right? So, oh, but wait, f of x is not going to be gamma, right? So let's put in here R minus gamma. So f of x is either less than gamma or f of x is greater than gamma. So f of x belongs to A or B, right? Now let's look at y is. So we've got that it's disjoint. So A and B are disjoint. We've got that. We've got that f of M is equal to A union B. Now we need to show that A and B are proper. Why are A and B proper? Subsets of f of M. Because P belongs to, f of P belongs to A, and f of Q belongs to B, right? F of P belongs to A, and f of Q belongs to B. So A isn't empty, and A is not f of M. Why? Because A doesn't include f of P, right? So A is proper. Similarly, B is a proper subset. Okay. Now the last thing we need to do is we need to prove that A disjoint union, we need to prove that the A's and the B's are cloven. So A, B, cloven in f of M. Well, of course they're going to be cloven because how do we get the open subsets? By the inheritance principle. You get an open subset if it is an open set in R intersected with your set, right? So clearly A is open in f of M because A is equal to an open set intersect f of M, right? So this is by the inheritance principle. Negative infinity to gamma, yeah? So because this is open in R, why is it open in R? That's something that you should be able to prove very easily. So I'll put that in there. Why is it open in R, right? But it is open set in R. Open set intersect with Fm is going to be open in f of M. All right. And then similarly, B is open in f of M. Right. So if you have two open sets and their union is equal to, their disjoint union is equal to f of M, then those sets have to also be cloven because B is actually going to be f of M. So say note B is equal to points in f of M that aren't in A, and A is equal to points in f of M that aren't in B, right? So if A is open in f of M, then B is closed in f of M. Okay? So we have a separation of f of M This is a contradiction. Why is this a contradiction? M is connected, F is continuous, F of M should be connected. Predicts F continuous plus M connected implies F of M connected. Okie dokie. So we'll pause for now and take a break.